All right, I want you to picture something for a second. Imagine looking exactly 5,200 light years away, deep into the Monosaurus constellation. If you could somehow see that far with perfect clarity, you wouldn't just see a random scattering of static stars. No way. You'd actually be front row to a violent, dynamic masterpiece that is currently being painted right across the night sky. Welcome to today's Explainer. We're putting our focus on an absolutely incredible celestial target, Caldwell 49, though you probably know it better as the Rosette Nebula. What we're looking at here is a massive, 100 light-year-wide canvas of violent, beautiful cosmic interactions. Today, we're going to break down exactly how this stunning structure is formed, driven, and shaped by the incredible forces hidden deep inside it. Okay, let's dive straight into this. Just take a second to absorb the sheer scale and the vibrant colors going on here. This is a newly recreated composite from the SDSS-V local volume mapper, combined with WISE dust maps, and honestly, it's just breathtaking. But since we're here to really understand how things work, we know there's some hardcore science behind every single hue and shadow. We aren't just looking at pretty space clouds. We are looking at a localized, intense battlefield of stellar radiation and interstellar gas. Part 1. A cosmic masterpiece and the central engine. To truly grasp what's happening in this masterpiece, we need to transition from just admiring the art to actually understanding the artists. We're talking about the massive stars that act as the roaring engine for this entire glowing structure. Let's ground ourselves real quick with a definition. Caldwell 49 is what astronomers call an H2 region. Basically, this means it isn't just some static cloud of dust hanging out in space. It's a highly active region of interstellar gas that's being heavily ionized by intense ultraviolet radiation pouring out from young, supermassive stars. The gas is literally being energized and blown apart, which is exactly what causes it to glow so brightly. Now, what's really interesting here is right in the center. Notice that massive hollowed-out dark cavity, the one populated by those specific stars marked in yellow and cyan. Those are the O and B-type stars of the NGC 2244 star cluster. At only about 2 million years old, which is just a blink of an eye in cosmic terms, this cluster is the absolute powerhouse. It's the central engine of the entire nebula. Without these specific stars, the Rosette Nebula simply wouldn't exist the way we see it. The most massive of these stars, specifically the rare, incredibly hot O-type ones, act essentially like a giant cosmic snowplow. They're unleashing ferocious stellar winds that expand outward at a staggering 56 kilometers per second. To put that in perspective, that's fast enough to cross the entire United States in a couple of minutes. This constant, relentless pressure blows a massive hot bubble into the surrounding space, physically hollowing out the center of the nebula and pushing gas and dust away to create that central cavity. Section 2, the colorful battleground, gas, dust, and bubbles. And this brings us right to the core focus of our explainer. We're going to look at the violent, super colorful interaction between this rapidly expanding bubble and the cold space surrounding it. So let's decode these colors, because they aren't just for show. They tell us exactly what kind of battle is happening and where. The blue and green regions represent ionized oxygen and hydrogen alpha. They trace the highly ionized, incredibly energetic gas right near that super hot center. But as you move outward toward the edges, you see that vibrant red. That red traces sulfur, which requires much lower energy to glow. So just by reading the colors, we can map the whole transition from the intensely hot, irradiated core all the way to the cooler, lower energy boundaries of the expanding bubble. And this brilliantly illustrates what happens when an unstoppable force hits an immovable object. On the left, we've got the thermal emission of dust, and on the right, the emission of molecular carbon monoxide gas. Notice how they form a rigid, almost unbroken shell entirely around the ionized center. This gray dust and glowing molecular gas are acting as a dense physical wall, aggressively resisting those 56 km/s stellar winds that are trying so hard to push past them. So we end up with this incredible contrast that completely defines Caldwell 49. On one hand, you've got the central cavity, highly ionized, almost completely cleared of dust, and completely dominated by the relentless UV radiation of massive O-type stars. On the other hand, you have the molecular edges, thick, dense walls of molecular gas and dust defined by mid to low ionization, just stubbornly shielding the outer cloud from total destruction. Part 3, Mapping the Unseen. Now, to truly appreciate how we even know all of this, we need to briefly pause the awe for a second and look at the incredible detective work required to map a structure this complex in 3 dimensions. Enter the SDSS-V Local Volume Mapper, or LVM for short. This instrument is a literal game changer. It doesn't just snap pretty pictures, it maps the actual physical properties of the interstellar medium. For this study alone, it captured over 33,300 spatially resolved spectra. By combining this optical data with infrared and submillimeter observations, astronomers can quite literally see the invisible structures of the universe layer by layer. It's like having X-ray vision for deep space. Which leads us to one of the most fascinating discoveries of the whole thing. If you look at the emission line ratios here, you'll notice it's not perfectly symmetrical. There's a really distinct north-south asymmetry in the dust extinction. What this data proves is that the nebula isn't a perfect sphere like a balloon. Instead, we are actually looking at an inclined molecular ring that is tilted about 30 degrees relative to us. The southern side is tilted toward us, meaning the central starlight passes through more intervening dust to reach our telescopes. Basically, we're looking at a massive, tilted cosmic donut. Because we have this ultra-high-resolution spectral data, researchers can zoom in on the specific boundaries where the gas and dust are fighting their hardest. Take a really close look at areas 3 and 4 here. You see those structures that look kind of like fingers reaching inward? Astronomers actually call those elephant trunks and globules. They are incredibly dense towers of dust that are physically fighting against photoevaporation. They're basically the last bastions of the original molecular cloud, standing strong against those brutal stellar winds. Section 4, Seeds of New Stars. And that resistance brings us right to the final act of our cosmic sculptor narrative, because there's a pretty incredible life-giving consequence to all this violent pushing and shoving happening at the edges of the nebula. I absolutely love this quote from the research because it captures the essence of it perfectly. The expansion of the ionized gas could be compressing the surrounding molecular gas, potentially inducing the formation of new stars. See, the expanding stellar bubble isn't just destroying the molecular cloud, it's actively squeezing it. And in space, when you squeeze molecular gas tightly enough, gravity takes over. The destruction is actually acting as a catalyst for creating new life. How cool is that? Let's move in and see how this builds in real time. If we zoom specifically into Area 4 on the western edge, we find NGC 2237. Now, this is an entirely different star cluster from the massive ones hanging out in the center. This is a cluster of young, low-mass stars embedded right in the thick, dense dust. They are forming precisely at the boundary where the expanding bubble is violently ramming into the molecular cloud. And if we shift over to the southeastern quadrant, marked by that green X, we find another embedded cluster known as PL97-2. Just look at how perfectly it sits in the high-density CO and dust region, just outside the absolute worst of the intense ionized gas. The high density of the dust here is literally acting as a shield, protecting these fragile little baby stars from the destructive UV radiation of the central engine. It's essentially a perfect cosmic incubator, forged by the very forces that are trying to blow it apart. So what does this all mean for us? Well, it leaves us with a rather profound thought to end on. As we look at the Rosette Nebula, at these massive central stars hollowing out a cavity, pushing dust to the edges, and triggering the birth of new, smaller stars in those protective dusty borders, we really have to look inward. Billions of years ago, before our solar system was fully formed, was our own sun born inside a dusty, expanding bubble exactly like this one, sculpted by the same colorful, violent forces? It's a fascinating question, and one that makes looking up at the night sky all the more incredible. Until next time, keep learning and keep looking up.